Right now, the most precise instrument humanity has ever built is sitting in a basement in Colorado. One atom, suspended in electric fields, ticking so accurately it wouldn't lose a single second across the entire age of the universe. But here's what nobody talks about. Move that clock 2 millimeters, and time literally flows at a measurably different rate, not in theory, on a readout. Which means time isn't a river you're floating in. It might be something the universe is quietly building, one interaction at a time from the inside. And if that's true, everything you think you know about now needs rethinking. If you're new here, hit like and subscribe. Pour yourself something warm, get comfortable, because tonight I'm walking you through how a chain of experiments from a frozen atom in Boulder to 2 entangled photons in Italy led physicists to a conclusion they've been circling for decades and never quite wanted to say out loud. And once you see that, the word now never quite means the same thing again. Now, let's ease into this. Part 1. The clock that shouldn't exist. There is a room in Boulder, Colorado that is colder than most of outer space, quieter than the inside of a mountain, and shielded from electromagnetic noise so thoroughly that the outside world essentially does not exist inside it. And in the centre of that room, suspended in a cage made entirely of electric fields, there is a single atom. One atom. Not a sample, not a crystal, not even a grain of anything you could see or touch. One aluminum ion, floating in a vacuum so extreme that it encounters fewer particles per cubic centimetre than the space between galaxies. And that single atom is ticking. Not ticking the way a wristwatch ticks, with gears and springs and the mechanical obstinacy of metal under tension. This atom ticks the way nature ticks at its most fundamental, by vibrating between 2 internal energy states at a frequency so high, so relentlessly stable, that the number it produces when you count those vibrations has become the most precise measurement of anything that human beings have ever made in the entire history of civilization. We are talking about a fractional uncertainty of approximately 10 to the power of -19. Written out, that is a decimal point followed by 18 zeros and then a 1, 19 decimal places of precision. To give you a sense of what that actually means, if this clock had been running since the Big Bang, since the very first moment of the universe, 13.8 billion years ago, it would not have gained or lost a single second by now. Not 1 second across the entire age of everything that has ever existed. Let that sit for a moment, because that number is not just impressive, that number is philosophically destabilizing. The clock lives at the National Institute of Standards and Technology, which most people know as NIST, and it belongs to a family of devices called optical atomic clocks. The particular architecture used here is called a quantum logic clock, and the way it works is worth understanding because it is genuinely one of the most elegant things that physics has ever built. The aluminum ion at the centre of this device is the actual timekeeper. Its internal quantum states oscillate at an optical frequency, meaning a frequency of light rather than microwave radiation, and that matters enormously. The cesium fountain clocks that define the international second from 1967 onward operate at microwave frequencies around 9 billion cycles per second. Impressive by any ordinary standard. But the aluminum ion operates at frequencies closer to 1 quadrillion cycles per second. 1 quadrillion. That is roughly 100,000 times higher frequency than cesium, and since precision in timekeeping scales with frequency, since a faster ticking clock can divide time into finer slices, the difference in accuracy between a cesium standard and this optical clock is not incremental, it is a revolution. But there is a problem. Aluminum ions are extraordinarily difficult to observe directly. You cannot simply shine a laser on this particular ion and read its state the way you can with other atomic species. The ion does not cooperate with that kind of probing. So the engineers at NIST built a workaround that sounds almost absurd until you understand quantum mechanics well enough to see why it is brilliant. They added a second ion, a magnesium or beryllium ion depending on the version, into the trap alongside the aluminum. This second ion acts as a logic qubit, a kind of quantum intermediary. The two ions are laser-cooled together until they are nearly motionless. Their quantum states become correlated through their shared motion in the trap, and then the logic ion acts as a readout device, transferring information about the aluminum ion state without ever directly disturbing the aluminum ion itself. It is like reading someone's mind by asking their best friend a question. Indirect, delicate, and extraordinarily effective. The result is a clock that does not just keep time in the ordinary sense, it measures the local flow of space-time. Here is where the story begins to get genuinely strange. In 1915, Albert Einstein published the general theory of relativity, and one of its consequences, a consequence so mathematically airtight that it has never been seriously challenged, is that time flows at different rates depending on gravitational potential. The stronger the gravitational field, the slower time moves. This is called gravitational time dilation, and at human scales, the effect is tiny. Near the surface of the Earth, you have to climb roughly 1 kilometre in altitude before the difference in gravitational potential becomes significant enough to matter for most purposes. GPS satellites deal with this correction constantly. They run fast by about 38 microseconds per day compared to clocks on the ground, and without compensating for that drift, your phone's navigation would accumulate errors of several kilometres per day. But 38 microseconds per day across hundreds of kilometres of altitude, that is a relatively gentle gradient. That is Einstein's theory operating at scales we can intuitively almost grasp. What the NIST optical clock revealed is something different, something that forces a much more uncomfortable question about what time actually is. In 2021, physicists at JILA, which is a joint research institute affiliated with the University of Colorado Boulder and NIST, published results showing that they could measure gravitational time dilation across a vertical distance of just 1 millimetre. Not 1 kilometre, not 1 metre, 1 millimetre, the height of a pencil tip. They used a cloud of about 100,000 ultra-cold strontium atoms arranged in an optical lattice, a kind of crystal made of laser light, and they demonstrated that atoms at the top of that millimetre-scale cloud were ticking measurably faster than atoms at the bottom because they were sitting at a slightly higher gravitational potential. The general relativistic effect was real, confirmed, and detectable across a distance smaller than the width of a grain of rice, and the NIST aluminum ion clock pushes this further still. At its level of precision, the clock is sensitive enough that physically lifting the apparatus by about 2 centimetres, roughly the width of your thumb, produces a detectable shift in its tick rate. You pick up the clock, you move it the width of a thumb, and time flows differently at the new position than it did at the old one. Not metaphorically, measurably. The numbers change. So now we have a device so precise that it is measuring not time in the abstract sense of duration, but variations in the local geometry of space-time at millimetre and centimetre scales. The clock is detecting the curvature of the universe in a laboratory in Colorado, using one atom and a laser. At this point, most science communication about atomic clocks stops and says something like, "Isn't physics incredible?" and moves on. But there is a question lurking underneath all of this precision that almost never gets asked, and it is the question that will drive everything we discuss tonight. If a clock measures differences in the rate of time flow between two locations separated by 2 centimetres, what exactly is the thing that is flowing at different rates? What is it that the clock is measuring? Not how, that part we understand in extraordinary mathematical detail, but what? Because here is the thing, physics is extraordinarily good at describing the behaviour of time. It can tell you how time dilates under gravity, how it slows near a massive object, how it becomes entangled with space in a 4-dimensional geometry. Physics can tell you how time behaves in virtually any scenario you care to name. What physics cannot tell you, what physics has, somewhat embarrassingly, never been able to tell you, is what time is. Not in the way you would explain what water is, what light is, what a particle is. Time gets described by its behaviour. It gets measured by its effects. It gets incorporated into equations as a variable. But the question of what it actually is, of what kind of thing it is in the fabric of reality, has no agreed answer. Not in 1925 when quantum mechanics was born, not in 1915 when general relativity arrived, and not in 2025 when we can measure it 19 decimal places out. We built a ruler so precise that it started questioning what a ruler is, and the answer to that question, the real answer, the one hiding in the mathematics and the experiments, is so strange that it will reframe everything you thought you understood about the word now, about the word past, about the word before. Because what physicists are beginning to confirm through experiments that have only become possible in the last few years is that time is not a river flowing through the universe. It is not a backdrop against which events occur. It is something the universe generates, from the inside through the act of physical systems interacting, recording, and relating to each other. Time, it turns out, may be something that happens to reality rather than something reality happens inside of. But to understand how we got to that conclusion, and why the clock in Boulder is the perfect starting point, we need to spend a moment with a crack in physics that has been there for over a century, hiding in plain sight, never quite fixed, always papered over with equations precise enough that no one asked the embarrassing question out loud. Until now. Part 2, the question nobody asks. Physics is, in many ways, the most precise and successful intellectual enterprise in human history. Its predictions match reality to more decimal places than any other branch of knowledge. It has given us lasers, semiconductors, nuclear reactors, GPS satellites, and a picture of the cosmos from fractions of a second after the Big Bang to the large-scale structure of galaxy filaments spanning hundreds of millions of light years. By almost every measurable standard, physics works, and it works astonishingly well, which is why it is so strange that at the centre of all of it, embedded in every equation and every experiment and every theory from Newton to Einstein to Feynman to the present day, there is a variable that nobody has ever actually defined. Not in a satisfying way. Not in the way that you can define a meter as the distance light travels in a specific fraction of a second, or define temperature as the average kinetic energy of particles in a system. At the foundation of physics, running through everything like a wire you cannot remove without the whole structure collapsing, there is a variable called t, time. And physics, for all its precision, does not tell you what t actually is. This is not a complaint about physics. It is not a failure in the ordinary sense. It is more like a puzzle that becomes more visible the more carefully you look at it. And the philosopher-physicist who has done the most to make this puzzle visible, to name it clearly and without embarrassment, is an Italian theoretical physicist named Carlo Rovelli. Rovelli, who works at the Aix-Marseille University and is perhaps best known to general audiences for his book called The Order of Time, has spent decades pointing at the gap between physics and philosophy when it comes to time, and his observation is deceptively simple. He says something to the effect of, "We know in extraordinary detail how time behaves. We do not know what it is. Think about how time shows up in physics, and you will start to see the circularity he is pointing at. Ask a physicist what time is, and they will say something like, 'Time is what clocks measure.' That is actually the operational definition. It is not informal or approximate. It is the official answer that emerges from both special and general relativity. Time is what a clock measures. Time is the reading on an ideal clock located at a specific event in space-time. That is it. That is the definition." But now ask, what is a clock? And you will get an answer that goes something like, a clock is a device that measures time. Or more technically, a clock is a physical system that evolves in a regular, repeatable way, such that you can track elapsed time by counting its cycles. Do you see the problem? Time is what clocks measure. Clocks are things that measure time. The definition is circular. It has always been circular, and for most practical purposes that circularity does not matter at all. For building GPS satellites or atomic clocks, or synchronizing international financial systems, the operational definition works perfectly. You pick a physical process, the oscillation of a cesium atom, the vibration of a quartz crystal, the swing of a pendulum, and you call that process a clock, and whatever it counts is time, and you go home. It works. It works beautifully. But here is where the question becomes more than academic. Isaac Newton, who essentially invented the mathematical framework of classical physics, was perfectly explicit about what he believed time to be. He wrote that absolute, true, and mathematical time flows equably without relation to anything external. Time, for Newton, was a universal backdrop. It existed independent of matter, independent of clocks, independent of observation. It was the stage on which physics happened, and it flowed the same way everywhere, for everyone, always. One clock, one rate, one now for the whole universe. That version of time was completely destroyed by Albert Einstein in 1905 and 1915. Special relativity showed that simultaneity is not universal. Two events that are simultaneous for one observer can be sequential for another moving at a different velocity, and both observers are equally correct. There is no fact of the matter about which is right, and general relativity went further, showing that time is not just relative between observers, but is literally curved by the presence of mass and energy. Time slows near massive objects. Time is part of a four-dimensional geometry that gets warped and bent by matter. There is no universal clock. There is no universal now. Each trajectory through space-time has its own proper time, its own personal elapsed duration, and none of them is more fundamental than any other. So Einstein destroyed Newton's absolute time. But Einstein did not replace it with a definition of what time is. He replaced it with a description of what time does. Time curves. Time dilates. Time is relative. Time is geometry. These are all descriptions of behavior. They are phenomenally accurate descriptions. But they do not answer the question of what kind of thing is behaving this way. The operational definition, time is what clocks measure, is honest in its limitations. It says, we will not make claims about the ultimate nature of time. We will only describe what happens when you measure it. In a sense, it is the most scientifically rigorous position available. But it also means that the central variable in every equation of physics, from Newton's second law to Schrödinger's equation to Einstein's field equations, is something that physics has quietly decided not to define in terms of anything more fundamental. This is what was always lurking beneath the surface. The aluminum ion clock in Boulder does not change this situation by being more precise. But it does something that precision at lower levels never quite accomplished. It makes the strangeness undeniable. When your clock is good enough to detect changes in the rate of time across 2 centimeters of height, you are no longer just measuring duration. You are measuring something that varies across space, something that has a local value at each point in the universe, something that is, in a very real sense, a property of the geometry of the place you are standing rather than a universal backdrop behind the universe. And that realization, time is not the stage. Time is part of the set, and it changes from one square foot to the next, is the realization that forces the next question. If time is not universal, and if physics cannot define it beyond saying it is what clocks measure, and if precision measurements are now showing us that even the rate of time is a local property of geometry rather than a global constant, then maybe the whole framework of thinking about time as a pre-existing thing that flows is wrong. Maybe time is not an ingredient of the universe, maybe it is a product, something that the universe generates internally, through specific physical processes, rather than something the universe is built inside of. That is the central idea we are tracking tonight, and the evidence for it has been accumulating from multiple directions simultaneously, from quantum mechanics, from thermodynamics, from gravity, from information theory, and from experiments that were simply not possible until we built instruments precise enough to see the cracks. Time is not something you're inside of. Time may be something that is happening around you, generated by the same physical processes that generate everything else. And the first indication that this idea was more than philosophy came not from the equations of the future, but from a series of experiments that were already pointing this way decades before anyone wanted to admit it. Part 3. The first cracks were already here. In October of 1971, a physicist named Joseph Haffel and an astronomer named Richard Keating boarded commercial airliners in Washington, D.C. They did not have an elegant laboratory setup or a controlled experimental environment. What they had were 4 cesium atomic clocks, each one roughly the size and weight of a large suitcase, and airline tickets for flights circling the globe. One set of flights went eastward, in the direction of Earth's rotation. Another set went westward, against it. The clocks flew around the entire planet while a reference clock sat on the ground at the United States Naval Observatory, ticking steadily in one place. When Haffel and Keating landed and compared their airborne clocks to the ground clock, they found exactly what Einstein's equations predicted they would find. The clocks disagreed, not by manufacturing defects, not by measurement error. They disagreed because time itself had flowed at different rates for the clocks depending on their velocity and their altitude. The eastward flying clocks had lost time relative to the ground clock. The westward flying clocks had gained time. The exact amounts, measured in nanoseconds, matched the predictions of special and general relativity to within the experimental uncertainties of the instruments available in 1971. This was not a thought experiment. This was not a mathematical derivation on a blackboard. This was 4 metal boxes full of oscillating cesium atoms flying around the world on TWA and Pan-American flights, and they came back with different times because time is not universal. Time bends. Time varies. Time is a local phenomenon, not a global constant. And if that still sounds like an esoteric physics result disconnected from everyday life, consider your phone. When you open a navigation app and ask it to route you somewhere, that app is talking to a constellation of satellites in medium Earth orbit, roughly 20,000 kilometers above the surface. Those satellites carry atomic clocks, and those clocks are running fast relative to clocks on the ground by approximately 38 microseconds per day. That is 38 millionths of a second. Tiny, barely imaginable, but multiply 38 microseconds per day by the speed of light, because GPS works by measuring how long signals take to travel from satellites to receivers, and that tiny discrepancy translates to a positional error of roughly 11 kilometers per day. Every single day, without the relativistic corrections built into the GPS system software, your navigation would be 11 kilometers off. Within a week, you would be navigating to the wrong country. Every time you use Google Maps, you're relying on the fact that Einstein was right about time dilation. The everyday infrastructure of modern civilization is built on the assumption that time flows at different rates in different places, so the cracks in the idea of universal time were not discovered yesterday. They were not uncovered by the latest generation of ultra-precise quantum clocks. They have been there for over half a century, measurable with the technology of 1971, baked into the engineering of systems that billions of people use every day without giving it a second thought. The aluminum ion clock in Boulder did not create the problem of time's variability. It intensified it. It pushed the measurable scale of time variation down from kilometers to millimeters, from continents to tabletops, and in doing so it made the question impossible to ignore at the conceptual level. Because here is what the millimeter scale JILA measurement really means. It is not just a technical achievement, though it is certainly that. It is a demonstration that your own body is a relativistic object. The atoms in your head are ticking very slightly faster than the atoms in your feet. You're not a single unified entity moving through time at a single rate. You're a collection of local clocks, each one running at the rate determined by its precise gravitational potential, and those rates differ slightly from your scalp to your soles. The difference is far too small to matter biologically, but it is real. You are, in a measurable physical sense, temporally extended, stretched across a tiny but non-zero gradient of space-time curvature, with different parts of you inhabiting very slightly different flows of time. And now consider what that means for the idea of a universal now. If time runs at different rates in different locations, then the concept of a single moment that is simultaneously now for your whole body, let alone for the entire universe, is not just philosophically problematic, it is physically incoherent. There is no universal now. There is only the local flow of time at each specific location in space-time. There is only what a clock at that exact position would read. The present moment is not a global property of the universe. It is a local property of wherever you happen to be. Newton's absolute time, the universal backdrop, the global clock, the single river of duration carrying everything along, was already dead before the 21st century began. What the current generation of experiments is doing is something far stranger. They are not just confirming that time is variable, they are starting to suggest that time, as we normally conceive of it, might not exist at the fundamental level at all, that the experience of temporal flow, of before and after, of past and future, might be something that emerges from physics rather than something physics operates within. And to understand how that idea became scientifically serious rather than merely philosophical, we need to follow the arrow. Because while the variability of time is well established, the question of why time has a direction, why it flows from past to future and not the other way around, turns out to be even more disturbing. Part 4. The arrow of time is an accident. Here is a fact about physics that sounds impossible but is completely true. Almost every fundamental equation in physics works equally well whether you run time forward or backward. Take the equations of Newtonian mechanics. Take Maxwell's equations for electromagnetism. Take Einstein's field equations for general relativity. Take the Schrödinger equation of quantum mechanics, which governs the evolution of quantum systems. In all of these frameworks, if you replace the time variable t with negative t, if you mathematically reverse the direction of time, the equations remain valid. They do not break. They do not produce absurdities. They continue to describe physical processes that are, in principle, allowed. A billiard ball rolls across a table, bounces off the cushion, and comes to rest. If you filmed that and played it in reverse, the reverse film would show a ball spontaneously beginning to move, bouncing off the cushion and rolling across the table. That looks wrong to you. You can tell immediately which version is the real recording and which is the reversed one. But here is the thing. The equations of mechanics do not know which is which. As far as Newton's laws are concerned, both versions are physically possible. The laws themselves have no preferred direction of time. They are, in the language of physics, time-symmetric. So if the laws of physics do not care which direction time runs, where does the arrow come from? Why do you experience time as flowing in one direction? Why does a broken egg not spontaneously reassemble itself? Why does heat flow from hot objects to cold ones and not the reverse? Why does the universe seem to have a past that is fundamentally different from a future, more ordered behind you, more disordered ahead of you, if the laws governing every particle in the universe are equally happy to run in either direction? The answer to this question was worked out in the 19th century by an Austrian physicist named Ludwig Boltzmann, and it is one of the most beautiful and most unsettling ideas in all of science. Boltzmann showed that the direction of time is not built into the laws of physics, it is a consequence of statistics. Specifically, it is a consequence of the relationship between the number of possible microscopic arrangements of a system and the macroscopic properties we observe. Think about a glass of water with an ice cube in it. Initially, the ice is cold and solid, the water is warm and liquid, and the system is in a relatively organized state. You can describe it compactly by saying there is a distinct ice cube in one corner and warm water elsewhere. As time passes, the ice melts, the temperature equalizes, and the final state is a glass of uniformly cool water. That final state is harder to distinguish in detail. The molecules are more uniformly distributed, the energy is more evenly spread, and the number of microscopic arrangements of the molecules that would look like that uniform state is astronomically larger than the number of arrangements that would look like a distinct ice cube. This measure, the number of available microscopic configurations, is entropy, and Boltzmann showed that the second law of thermodynamics, which says entropy always increases, is not a fundamental law of nature, but a statistical near certainty. It is overwhelmingly, almost inconceivably more likely for a system to evolve toward higher entropy states simply because there are so many more of them. The reason ice melts is not that any law forces it to. It is that the odds of spontaneous reassembly are so astronomically small that in the entire age of the universe you would not expect to see it happen once. And here is where the idea of time's direction becomes philosophically unsettling in a new way. If the laws of physics are time-symmetric, and if the arrow of time is just a statistical tendency, then the arrow of time is not fundamental. It is not built into the universe at the level of laws. It is an emergent property that appears because the universe started in a state of unusually low entropy, unusually high order, and has been statistically drifting toward higher entropy ever since. David Albert, a philosopher of physics at Columbia University, has thought about this more carefully than almost anyone, and he calls the starting condition the past hypothesis. The universe, in its earliest moments, was in a state of remarkably low entropy, extraordinarily ordered, and everything, every irreversible process, every experience of temporal direction, every memory, every causal chain you have ever experienced derives from that initial low entropy condition. The arrow of time is an arrow pointing away from an unusual beginning. Now here is the problem with this. The laws of physics are time-symmetric. That means you can equally well run the argument backward. You can ask, why is the past low entropy rather than the future? And the honest answer is that if you did not already know which end of time you were on, the equations alone would not tell you. The arrow of time is not in the equations. It is in the initial conditions. It depends on the fact that the universe started in a special state. And that raises a question physics has struggled with ever since Boltzmann. Why did the universe start in a low entropy state? What made the beginning of everything so unusually ordered? No one has a fully satisfying answer. Some physicists argue it is just a brute fact, and unexplained given that we accept and build on. Others argue it must be explained by a deeper theory. But for our purposes tonight, the crucial point is this. Time's direction is an accident of initial conditions. It is a statistical artifact of where the universe began, not a fundamental feature of physical law. The universe did not have to have an arrow of time. It has one because it started in an improbable state and has been randomly drifting away from that state ever since. The past is different from the future not because some law mandates it, but because the universe got lucky, or unlucky, or however you want to frame the extraordinary specificity of its beginnings, and that realization opens a door to an even stranger question. If the arrow of time is statistical and emergent rather than fundamental, then it must be produced somewhere, by something. There must be a physical process that generates irreversibility, that turns the time-symmetric laws of physics into the time-asymmetric experience of before and after. What is that process? Where does irreversibility actually come from? And the answer, when you find it, connects directly to the central thread of everything we are discussing tonight. The idea that time is not something the universe contains, but something the universe continuously generates through specific physical acts. Part 5. Observation is not passive. In 1961, a physicist named Rolf Landauer was working at IBM's research division and thinking about a problem that most of his colleagues considered either too obvious to be interesting or too philosophical to be physics. The problem was this. What is the relationship between information and the physical world? Not in the vague, hand-waving sense that information requires physical objects to carry it. In the precise, quantitative, thermodynamic sense. Does manipulating information, storing it, copying it, erasing it, have measurable physical consequences? Does the act of knowing something about the world cost anything in the currency that physics cares about most, which is energy and entropy? Most physicists at the time, if they thought about it at all, assumed the answer was essentially no. Information felt like an abstract thing, a mathematical object, a pattern. And patterns, the intuition went, do not have thermodynamic weight. You can copy a pattern without using energy. You can store a pattern without generating heat. The pattern is not the thing, it is the description of the thing, and descriptions float free of thermodynamics. Landauer showed, in a paper that most of his contemporaries ignored for years, that this intuition is completely wrong, and the argument he made was so clean, so direct, so difficult to escape once you understood it, that it eventually became one of the foundational results in the physics of information. It is now called the Landauer principle, and it connects two domains of physics that had never been formally connected before: information theory and thermodynamics. The bridge between them turns out to run directly through the question of time. Here is the argument. Information, Landauer said, does not exist in the abstract. It cannot. Every bit of information, every yes or no, every 1 or 0, every recorded fact about the state of any physical system anywhere, must be encoded in some physical substrate. It has to live somewhere. In the orientation of a magnetic domain on a hard drive platter, in the charge state of a capacitor in a RAM chip, in the energy level of an atom in a quantum memory, in the pattern of synaptic connections in a biological brain. There is no such thing as information that is not instantiated in physical matter. Information is always, necessarily, a property of something physical. And because it is physical, doing things to information means doing things to physical systems, and doing things to physical systems has thermodynamic consequences. Most operations on information are thermodynamically cheap. Reading a bit costs essentially nothing. Copying a bit from one location to another costs essentially nothing. Even writing a new bit into a system that is already in a known state costs essentially nothing. But there is one operation that has an irreducible thermodynamic cost: erasing information, genuinely erasing it, taking a bit that was in some unknown state, either 0 or 1, and resetting it to a known state, say 0, permanently losing track of what it used to be. That operation cannot be done for free. It requires releasing a minimum amount of heat into the environment. The formula is exact. The minimum energy cost of erasing one bit is Boltzmann's constant times the temperature of the environment times the natural logarithm of 2. At room temperature, this is a fantastically tiny number, around 3 times 10 to the negative 21 joules, so small that it is completely irrelevant in any practical engineering context. Your laptop dissipates vastly more energy than this minimum with every operation, not because of Landauer's limit, but because of the inefficiencies of real silicon transistors. The Landauer limit is so far below the actual energy costs of real computing that it might seem like a purely academic result with no practical significance. But here is why it matters enormously, regardless of its practical engineering implications. It is not 0. It cannot be 0. And the reason it cannot be 0 is profound. When you erase a bit, when you take a system that was in one of 2 possible states and force it into a definite single state, you are reducing the number of possible microscopic configurations of that system. You are decreasing its entropy locally. And the second law of thermodynamics, which says the total entropy of a closed system cannot decrease, demands compensation. The entropy you remove from the information-bearing system must go somewhere. It goes into the environment as heat. Erasure of information is, unavoidably, an entropy-generating process. It is a thermodynamic event with a minimum energy cost that no engineering ingenuity can eliminate, because it is not a cost of our current technology. It is a cost written into the laws of physics. This was confirmed experimentally in 2012 by a team at the University of Stuttgart who used a microscopic particle suspended in a laser trap to perform single-bit erasure and directly measure the heat released. Landauer was right. Information erasure generates entropy in exactly the amount the principle predicts. The connection between information and thermodynamics is not a metaphor. It is quantitative, measurable, and real. Now take this result and ask a question that Landauer himself gestured toward, but that has been developed much more fully in the decades since. What happens thermodynamically when a physical system makes a measurement? When a clock records a tick? When a detector registers a particle? When any physical device observes something about the world and stores the result? What is the thermodynamic status of that act? The answer, through the lens of Landauer's principle, is that measurement is not passive. It is not a neutral act of witnessing that leaves the universe unchanged. A device that measures something must physically couple to the thing being measured, it must interact with it, exchange energy or momentum or some other physical quantity with it. It must record the result in some physical medium, which means encoding information in a physical substrate. And at some point in the process, it must update its internal state to reflect what it found, which in general involves overwriting a previous state, which is erasure, which generates entropy. Every observation is a thermodynamic event. Every record creates irreversibility. Every measurement leaves a physical scar on the universe, a tiny increment of entropy, a small and permanent asymmetry between the state before the measurement and the state after it. The world, having been observed, is microscopically different from the world that has not been observed, not because consciousness has intervened, not because anything mystical has happened, because a physical system has coupled to another physical system and made an irreversible record of what it found, and irreversible records cost entropy, and entropy is the currency of time's direction. This is the connection that matters. The arrow of time, the reason the past is different from the future, the reason you remember yesterday and not tomorrow, the reason causes precede effects, is built from irreversibility. Boltzmann showed us that. The second law of thermodynamics is a statement about the overwhelming statistical tendency of systems to move toward higher entropy states, because there are so many more of them. The arrow points from lower entropy to higher entropy, from the unusual initial conditions of the Big Bang toward the increasingly disordered future. That arrow is made of irreversibility, and Landauer's principle tells us that irreversibility is made of records. Every time any physical system makes an irreversible observation of another physical system, every time information is encoded in a physical medium in a way that cannot be perfectly undone, entropy is generated and the arrow of time is extended by one more notch. The before and after that you experience as temporal flow are, at the physical level, a trail of thermodynamic scars. Records written into matter, observations encoded in physical substrates. The arrow of time is, in this precise technical sense, a product of the act of physical memory. Think about what this means for the question we started with. We asked where time comes from, specifically where its direction comes from. Why does it flow one way and not the other, given that the fundamental laws of physics are time-symmetric and equally happy to run in either direction? The answer is beginning to come into focus. Time's direction is not built into the laws, it is built into the records. It is built into the irreversible physical memories that systems make of each other, the entropy generated every time the universe pays physical attention to itself and writes down what it found. You are, in this sense, a time-generating machine, not in some poetic or metaphorical sense, literally. Every memory your brain forms is a physical record, an irreversible encoding of information in neural tissue that generates entropy and extends the arrow of time locally. Every perception you have is a measurement, a physical coupling between your sensory apparatus and the world that costs thermodynamic irreversibility and creates a before and after that did not exist before the perception happened. You're not moving through time. You are, in the most direct physical sense, making time as you go. Every observation you make is a small act of temporal creation, and this is not unique to you. It applies to every physical system that stores information, every DNA molecule recording the chemical history of a cell, every rock formation encoding the geological history of a landscape, every photon detector registering the arrival of light from a distant star, every quantum measurement apparatus in every laboratory on Earth. Wherever any physical system makes an irreversible record of the state of another physical system, time's direction is locally generated. The arrow exists because the records exist. The records exist because physical systems interact. And physical systems interact because that is what it means to be physical. These questions, where do records come from? What systems are making measurements? What is coupling to what and creating irreversible physical memories? Started as questions in information theory and thermodynamics. But they have been converging in recent years with questions at the frontier of quantum mechanics. Because it turns out that the relationship between observation, record-making, and the emergence of time is not just a thermodynamic story. It is a quantum mechanical story, and the experiment that demonstrated it most directly, that showed exactly where in a quantum system the arrow of time lives and what puts it there, happened not in a cosmology department or a theoretical physics institute, but in a small laboratory in Oxford, using a device so simple it barely looks like a clock at all. Part 6. The Oxford Experiment. The device does not look like a clock. It does not have a face or hands or even a digital display. It is a quantum dot, a tiny semiconductor structure, nanometers across, small enough that the rules of quantum mechanics govern its behavior completely rather than approximately. And the thing that makes it tick, in the loosest possible sense of that word, is an electron. One electron tunneling back and forth through a barrier that classical physics says it should not be able to cross at all. Every time the electron tunnels from one side to the other, the device registers a transition. Count those transitions, and you have something that behaves, in a limited way, like a clock. This is the system that Vivek Wadia and Natalia Aries at the University of Oxford built and studied in work published in 2025. And what they did with this quantum clock reveals something so fundamental about the nature of time's direction that it has forced a reassessment of where the arrow comes from. Here is what they found. When the quantum dot electron is in thermal equilibrium, when the system is sitting at some ambient temperature without being driven or pumped, the electron tunnels forward and backward at exactly the same rate. Transitions from state A to state B happen just as often as transitions from state B to state A. There is no preferred direction. The system is, in the language of thermodynamics, microscopically reversible. If you filmed the electron's behavior and played it backward, you would not be able to tell the difference from the forward film. The electron does not have an arrow of time. Its dynamics are perfectly time-symmetric, just as the fundamental laws of physics are. Now here is where the experiment becomes remarkable. Measuring the system, actually observing the electron, recording its transitions, making a physical measurement and storing the result, requires coupling the quantum dot to a measurement apparatus. And that measurement apparatus is a physical system operating at a temperature above absolute zero, which means it has thermal fluctuations, which means it dissipates energy, which means it generates entropy. Wadia and Aries carefully measured the energy cost of each individual measurement event, and they found something striking. The energy required to make a single measurement of the quantum dot transition was approximately 10 to the 9th power, 1 billion times, larger than the energy of the transition itself, 1 billion times larger. To observe something that tiny, using the most delicate measurement technology available, the act of looking consumed 1 billion times more energy than the thing being looked at. And all of that energy went where? Into entropy, into heat released into the environment of the apparatus, into thermodynamic irreversibility, into the arrow of time in the measuring device. But the quantum dot itself, the electron, the actual physical system doing the tunneling was perfectly reversible. The irreversibility, the temporal direction, the sense of before and after was entirely in the measurement record. It was in the apparatus. It was in the physical memory of the observer. Vivek Wadia described this result in terms that are worth sitting with carefully. The arrow of time in this experiment is not in the quantum system itself. It is in the record of the quantum system. The electron does not experience a before and an after. The electron tunnels back and forth symmetrically, with no preference for direction, with no intrinsic timeline. The arrow of time appears only when something external to the electron, a detector, an apparatus, a measuring system couples to it and makes an irreversible record of what the electron did. The before and after exist in the notebook, so to speak, not in the thing being written about. Now think about what this means in the context of everything we have been building. The fundamental laws of physics are time-symmetric. The arrow of time is produced by the overwhelming statistical tendency of high-entropy states to outnumber low-entropy states. Landauer's principle tells us that making records generates entropy. And now the Oxford experiment shows, in a real physical laboratory with a real quantum device, that the time asymmetry of a physical process lives in the record of that process, not in the process itself. The electron has no arrow of time. The measurement record does. So let us say this very carefully. Time's direction, the fact that you remember the past but not the future, that causes precede effects, that you cannot unscramble an egg, does not appear to be a property of the fundamental dynamics of physical systems. It appears to be a property of the way physical systems record information about each other. The arrow of time is, in this sense, a product of observation. Not observation in the mystical or consciousness-based sense, but in the purely physical, thermodynamic Landauer principle sense. Whenever any physical system makes an irreversible record of the state of another physical system, time's direction is generated. Before and after are created by the act of physical memory. And this brings us to the edge of the strangest question. If time's direction depends on observation and record-making, what about time itself? Not just its arrow, but its existence. What happens to time, not just to its direction, but to its very presence as a parameter, when you zoom out to the larger scale, to the scale of the universe as a whole? Because at that scale, there is no external observer. There is nothing outside the universe to observe it and make records about it. The universe is all there is. And when physicists wrote down the equation that is supposed to describe the entire universe, the equation that should, in principle, replace Newton's laws and Einstein's equations at the most fundamental level, what they found in 1967 was something that stopped everyone cold. The equation did not have time in it. Part 7. The equation that removed time. There is a particular kind of problem in physics that does not announce itself as a crisis. It does not show up as a failed experiment or a measurement that contradicts a prediction. It shows up as a result that is technically correct, mathematically airtight, and yet somehow deeply, quietly wrong in a way that takes years to fully appreciate. A result that everyone acknowledges and nobody quite knows what to do with. A result that sits in the literature like a splinter, small, easy to work around, impossible to fully ignore. The Wheeler-DeWitt equation is that kind of problem, and to understand why, you need to understand what it was trying to do, and why the thing it ended up doing instead is one of the strangest facts in all of modern science. In 1967, a theoretical physicist named Bryce DeWitt sat down with a task that sounds straightforward when you state it, and turns out to be one of the hardest things physics has ever attempted. He wanted to write down the quantum mechanical description of the entire universe, not a particle, not a field, not a galaxy or a solar system or any subsystem within the cosmos, the whole thing, the wave function of everything, the single equation that, in principle, contains the complete quantum description of all of physical reality from the Big Bang to the present moment and beyond. To appreciate why this is hard, you need to know something about the two theories he was trying to combine. General relativity, Einstein's theory, published in 1915, describes gravity not as a force, but as the curvature of space-time. Mass and energy bend the geometry of space and time around them, and what we experience as gravitational attraction is simply objects following the straightest possible paths through that curved geometry. It is a theory of the large, of planets, stars, black holes, the expansion of the cosmos. It is smooth, continuous, deterministic. Given the distribution of matter and energy at one moment, general relativity tells you with complete precision what the geometry of space-time will be at every subsequent moment. Quantum mechanics, developed in the 1920s and refined through the rest of the 20th century, describes the behavior of matter and energy at the smallest scales. Particles, fields, atoms, the interactions between them. It is probabilistic rather than deterministic. It does not tell you exactly what a particle will do, only the probability of different outcomes. It is discontinuous. Quantum states can jump between values in ways that have no classical analogue. It is measurement dependent. The act of observation plays a fundamental role in determining what physical properties a system has. It is, in virtually every way, the philosophical opposite of general relativity. These two theories are the twin pillars of modern physics. Between them, they describe virtually everything we know about physical reality. Quantum mechanics handles the small, general relativity handles the large, and for most practical purposes, you never need both at the same time. Quantum mechanics is irrelevant when you're calculating the orbit of a planet. General relativity is irrelevant when you're calculating the energy levels of an atom. The two theories live in separate domains, and for most of the history of physics since the 1920s, physicists have been comfortable keeping them separate and ignoring the fact that they are, at a fundamental level, incompatible. But there are places where you cannot keep them separate, where you need both simultaneously, and where their incompatibility becomes not just a philosophical inconvenience, but a practical disaster. The centre of a black hole, where matter is compressed to infinite density in a region so small that quantum effects cannot be ignored. The very first moments of the Big Bang, where the entire universe was compressed into a space so tiny that it was simultaneously a quantum system and a gravitational system. At these extremes, you cannot choose between the two theories. You need a unified framework, a theory of quantum gravity, that contains both as limiting cases and remains coherent where both apply at once. Nobody has successfully built that theory. String theory is one attempt. Loop quantum gravity is another. There are others still. None of them is complete. None of them has produced unambiguous experimental predictions that have been tested and confirmed. The unification of quantum mechanics and general relativity remains the single greatest unsolved problem in all of theoretical physics. We do not know how to do it, and we have been trying seriously for nearly a century. What DeWitt did in 1967 was not solve this problem. He took one particular approach to it, a framework being developed in collaboration with John Wheeler, one of the most creative and far-ranging theoretical physicists of the 20th century, and he pushed it as far as it would go. Wheeler had been developing what is called the canonical quantization of gravity, an attempt to apply the mathematical machinery of quantum mechanics directly to the geometry of space-time. And the central object in this framework is the wave function of the universe, a quantum state that encodes the probability amplitude for the universe to be in any particular geometric configuration. DeWitt wrote down the equation that this wave function must satisfy. He applied the standard procedure of quantum mechanics, the mathematical technique of turning a classical equation of motion into a quantum wave equation, to the classical equations of general relativity. He did the calculation, he got an answer, and the answer had something missing: time. The equation he wrote down, now universally called the Wheeler-DeWitt equation, has no time variable in it. It describes the wave function of the universe as a function of the geometry of space, the distribution of matter and energy, the configuration of fields. But it does not describe how any of those things evolve over time. It does not say the universe was in configuration A at time 0 and configuration B at time 1 billion years. It simply describes a quantum state with no reference to when or how the state changes. The wave function of the universe, according to this equation, does not evolve. It is static, frozen, timeless. When you first encounter this, the instinct is to assume something has gone wrong, a mistake in the derivation, a missing term, some mathematical error that, once corrected, will restore the time variable and give you back the universe you're familiar with, the one that changes, that evolves, that has a history stretching back nearly 14 billion years. But the equation is not wrong. The absence of time is not a mistake. It is a direct mathematical consequence of what happens when you try to combine general relativity with quantum mechanics at the level of the whole universe. Here is the core of the issue as cleanly as I can state it. In general relativity, there is no preferred time coordinate. This is not a minor technical point. It is one of the theory's deepest features. Different observers, moving at different velocities or sitting at different gravitational potentials, have different notions of time. There is no universal clock. There is no single time variable that all observers agree on. Time is part of the geometry, and the geometry is different for different observers. When you try to write a quantum equation for a system that includes all possible observers, all possible geometries, all possible time coordinates simultaneously, as you must, when the system in question is the entire universe, the time variable cancels out. You're summing over all possible ways of slicing up space-time into moments, and when you sum over all of them, time disappears. This is the Wheeler-DeWitt equation. This is the quantum wave function of the cosmos, and it says the universe, at the most fundamental level of description, does not change, does not evolve, has no before and no after, has no time. Let that land properly. Because I want to be honest about how strange this is. This is not a fringe idea. This is not an eccentric proposal from the margins of physics. The Wheeler-DeWitt equation is mainstream. It is taken seriously. It is discussed in graduate courses in quantum gravity, and it has been sitting there since 1967 as a quiet, persistent, deeply uncomfortable feature of our best attempts to describe reality at the most fundamental level. The universe's own governing equation does not have time in it, and yet you are here. You are reading these words. You remember the words that came before these. You are anticipating the words that will come after. Every thought you have is a change. Every breath you take is a change. Every moment you experience as now replacing the previous now is, inescapably, a change. You are, in the most direct and undeniable experiential sense, a creature of time, radically, completely, constitutively temporal. Time is not something you occasionally notice. Time is the medium of your entire existence. Remove time from your experience and there is no experience left. The equation that describes everything you are made of says time does not exist at the fundamental level. This is not a solved problem. I want to be very clear about that, because there is a tendency in science communication to present open questions as more resolved than they are, to paper over the uncertainty with confident language and move on. The tension between the timelessness of the Wheeler-DeWitt equation and the lived reality of temporal change is, as of right now in 2025, one of the deepest and most genuinely unresolved questions in all of theoretical physics. The people who know this equation best disagree profoundly about what it means. Some say it means the equation is incomplete, that we need a better theory of quantum gravity, one that does not lose time in the process of combining general relativity with quantum mechanics, that the disappearance of time is a symptom of our current approach rather than a fundamental feature of reality, that when we eventually build the correct unified theory, time will be restored as a genuine fundamental variable, and the Wheeler-DeWitt equation will be seen as a useful but limited approximation that got something important wrong. Others say it means time is emergent, that the equation is correct, and the fact that it has no time at the fundamental level is telling us something true and important, that time does not exist at the bedrock of reality, but appears to exist at the level we observe, generated by some process that the equation itself does not make obvious. That the universe is, at bottom, timeless, and that everything we experience as temporal is a kind of higher-level phenomenon, real at our level, the way temperature is real, but not written into the deepest description. And then there is a third position, which is in some ways the most radical and in some ways the most elegant. It says the equation is fundamentally correct, that time is emergent, and that the process by which it emerges is something internal to the universe, something that happens between subsystems through their physical relationships and quantum correlations without requiring any external time variable at all. This is the position that points directly toward the work of Page and Wouters, which we are about to get to. It says the universe does not need time built in from the outside because it generates time from the inside through the act of its own parts paying physical attention to each other. What all three positions agree on is this: the naive picture of time as a universal backdrop, a river flowing through the cosmos carrying everything along with it, a single global clock ticking the same way for everyone everywhere. That picture is not what the Wheeler-DeWitt equation describes. Whatever time is, it is not that. And the equation has been telling us so since 1967 in the quietest, most mathematically certain way possible, waiting for the rest of physics to catch up with what it was saying. In 1983, two physicists finally started listening, and what they heard changed everything. Part 8. The 1983 idea that SAT ignored. Don Page was not a household name. He was not the kind of physicist who ends up on magazine covers or gives TED Talks that rack up millions of views. He was a careful, methodical theorist who had spent time working directly with Stephen Hawking, which tells you something about the level of the man, and in 1983 he was sitting with a problem that most of his colleagues were content to quietly ignore. William Wouters was in a similar position. A physicist who would later make foundational contributions to quantum information theory, one of the most consequential fields in all of modern science, Wouters in 1983 was young, rigorous, and deeply bothered by something that the equations seemed to be saying and that almost nobody wanted to hear. The thing they were both bothered by was the Wheeler-DeWitt equation. We talked about this earlier, the equation that Bryce DeWitt wrote down in 1967 when he tried to combine general relativity with quantum mechanics and produce a description of the entire universe at the quantum level. The equation that, when you actually look at it, has no time variable. The universe, according to this equation, does not evolve. It does not change. It is described by a static quantum wave function, a frozen mathematical object with no before and no after, no tick and no tock, no direction from past to future. From the outside, from a hypothetical God's eye perspective that could somehow see the universe as a whole, nothing is happening. The universe just is. And yet here you are, reading this, remembering the sentence before this one, anticipating the sentence after, experiencing with complete and utter certainty the sensation of one moment following another. The universe described by its own most fundamental equation is timeless. The experience of being inside that universe is inescapably temporal. Something is wrong, or something is missing, and in 1983 Page and Wouters thought they knew what it was. Their answer was this: time emerges from correlations between subsystems within the universe. Let me slow down on that, because it is one of those sentences that sounds simple and is actually one of the deepest ideas in modern physics. The key word is correlations, not flow, not passage, not the ticking of some cosmic master clock. Correlations, relationships, the way the state of one part of the universe encodes information about the state of another part. Here is how the argument works. Imagine you split the universe into two pieces. Call them A and B. It does not matter exactly what A and B contain. The argument is general, but let's say part A contains a clock of some kind, some physical system whose internal state changes in a regular trackable way. A pendulum, an oscillating atom, a spinning particle, anything whose states cycle through a predictable sequence. And part B contains everything else you care about, the system you want to describe, the thing you are trying to understand. Now, from the outside, from that God's eye view, neither A nor B is changing. They are both part of the total static wave function. The Wheeler-DeWitt equation is satisfied. Nothing is evolving. Externally, if you could somehow observe the entire universe at once, you would see a frozen quantum state, timeless. But now shift your perspective. Instead of asking about A and B together from the outside, ask about B from the inside. Ask, what is the state of B, given that A is in a particular state? What does B look like when the clock reads noon? What does B look like when the clock reads midnight? When you ask those conditional questions, when you look at B through the lens of what A is doing, something remarkable happens. B appears to change. B appears to evolve. The state of B is different depending on which state of A you condition on, and if you scan through the states of A in sequence, you get what looks exactly like temporal evolution of B. You get change. You get before and after. You get time, not because anything external is flowing, not because there is some master clock outside the universe ticking away, but because the quantum correlations between A and B, the entanglement between them, the way the state of one encodes information about the state of the other, generate the appearance of temporal evolution from the inside, even when the total system is completely static from the outside. Page and Wouters were saying something that almost sounds like a koan. The universe is frozen, and yet from inside the universe, everything moves. Both statements are true simultaneously. They describe the same physical reality from two different perspectives, and neither perspective is wrong. To make this feel less abstract, think about a photograph. A photograph is completely static. Nothing in it moves. From the outside, from the perspective of someone holding the photo, it is a frozen moment. But imagine you're a tiny, two-dimensional creature living inside that photograph. You cannot step outside it. You cannot see it whole. You can only see what is immediately around you and, across the image, the face of another person. Now suppose that person's face changes across different parts of the photograph, smiling in one region, neutral in another, tired in a third. From the outside, all of those expressions exist simultaneously in the frozen image. But from inside, if you can only access one region at a time, and you move through the photograph correlating your position with the expression you see, you would experience something that feels exactly like watching someone's mood change across a day. You would reconstruct a temporal sequence, not because time is flowing in the photograph, but because the correlations between your state and the other person's state, read out from the inside, produce the structure of before and after. That is what Page and Wouters were describing, except it is not an analogy. It is literally what quantum mechanics does when you work out the mathematics carefully. If you take a static total wave function, split it into an entangled clock subsystem and an observed subsystem, and ask conditional questions from the inside, conditioning on the clock state when you describe the rest, you get temporal evolution. You derive it. From nothing but correlations, from nothing but the quantum entanglement between the parts. Time in this framework is relational. It is not something the universe is inside of. It is something that parts of the universe generate for each other, through the quantum relationships between them. One part acts as a clock for another. The second part experiences something that, from the inside, is indistinguishable from temporal flow. And the experience of time passing, the sensation you have right now of one moment following another, is, in this view, the experience of those correlations being read out from your particular vantage point inside the system. When Page and Wouters published this in 1983, the response from the physics community was largely a shrug. Not because the idea was wrong, nobody found a serious mathematical flaw in it, but because it was so abstract, so far removed from anything testable, that most physicists filed it under interesting but untouchable and moved on. You cannot build an experiment around the entire universe. You cannot put the cosmos in a lab. You cannot step outside everything and check whether the total wave function is really static while the internal correlations are generating apparent time, or so everyone assumed. What nobody quite anticipated was how fast the tools would change. By the 2010s, experimentalists working in quantum optics and quantum information had developed the ability to do things with individual photons that would have seemed like science fiction to the physicists of 1983. They could prepare entangled quantum states with extraordinary precision. They could make conditional measurements, measuring one particle depending on the state of another, in ways that directly probe the structure of quantum correlations. They could, in short, build small laboratories that enacted the Page-Wouters mechanism on a miniature scale, using the simplest possible quantum system, 2 photons. And that is exactly what a team of physicists in Italy did. The setup was, on the surface, almost comically minimal. 2 photons prepared in an entangled quantum state, one designated as the clock, one designated as the universe, the system whose evolution you want to describe. From the outside, measuring the total 2-photon system together, the state was static, frozen, no evolution. The Wheeler-DeWitt picture confirmed in miniature. But from the inside, measuring the universe photon conditionally, depending on the state of the clock photon, the universe photon evolved. It changed. It moved through a sequence of states that, from the internal perspective, looked exactly like temporal progression. 2 perspectives, 1 physical system, timeless from the outside, evolving from the inside. The experiment did not just confirm a theoretical prediction. It did something harder to articulate but more important. It made the abstract concrete. It took an idea that had lived in the realm of equations and philosophical argument since 1983 and turned it into something you could point to, something that happened in a laboratory, something that produced data, time, not measured, not tracked, but genuinely generated from nothing but the relationship between 2 particles paying quantum mechanical attention to each other. The universe had been asked in the smallest possible way whether time could come from correlation rather than flow, and it had said yes. Part 9. Time created in the lab. Ekaterina Mareva is not a name that gets dropped at dinner parties. She's not a figure who has crossed over into popular culture the way Hawking did, or even the way figures like Neil deGrasse Tyson or Brian Greene have. She's a working physicist, a careful experimentalist, and in 2013 and 2014 she did something in a laboratory in Turin, Italy, that I would argue deserves to be talked about in the same breath as the double-slit experiment, the Michelson-Morley experiment, the discovery of the cosmic microwave background. One of those moments where someone points a piece of equipment at a question that was supposed to be unanswerable, and gets an answer anyway. What Mareva and her colleagues at the Istituto Nazionale di Ricerca Metrologica did was take the Page-Wouters mechanism, that theoretical proposal from 1983, the one that sat largely ignored in the literature for 3 decades because it was too abstract to test, and they built it. Physically, in a lab. They encoded it in photons, ran the experiment, collected the data, and found exactly what the theory predicted. Let that sink in for a moment. A theoretical framework proposing that time itself emerges from quantum correlations between physical subsystems, a framework that most physicists had filed under interesting but untestable, turned out to be testable, and it was right. Here is what they actually did. 2 photons were prepared together in an entangled quantum state. If you're not familiar with entanglement, the short version is this. 2 particles can be prepared in such a way that their quantum states are correlated at the most fundamental level. Measuring one instantly tells you something about the other, no matter how far apart they are. Einstein called it spooky action at a distance, and spent years trying to prove it was wrong. He was not successful. Entanglement is real, it is well established, and it is the resource that Mareva's experiment depended on. One of the 2 photons was designated the clock. The other was designated the universe, the system whose behavior you want to describe and track over time. Now, the first thing the team did was look at the system from the outside. They set up measurements that probed the total 2-photon state without singling out either photon for a special role, without conditioning on one to read the other. They just looked at both photons together as a combined system, the way a hypothetical external observer looking at the entire universe from outside would do. What they saw was nothing, or rather, nothing changing. The total quantum state of the 2 photons was static. It did not evolve. It sat there, a fixed entangled state, the same at one measurement as the next. From the outside, there was no time. The Wheeler-DeWitt picture, which says the universe's total wave function is frozen, was confirmed in miniature. 2 photons, 1 entangled state, no temporal evolution. The universe, at the level of its total description, has no clock. Then they changed the measurement. They introduced what you could call an internal observer, a measurement protocol that reads out the state of the universe photon not directly, not in isolation, but conditionally, depending on what state the clock photon is in. If the clock photon is in state 1, what is the universe photon doing? If the clock photon is in state 2, what is the universe photon doing then? Scan through the possible states of the clock photon in sequence and ask at each step what the universe photon looks like from that vantage point. And now everything changed. From this internal perspective, conditioning on the clock, reading the universe photon through the lens of where the clock was, the universe photon evolved. It was in one polarization state at one clock reading, a different polarization state at the next, a third state after that. It moved through a clear, trackable, directional sequence of states. From the inside, time was flowing. Things were happening. The universe was changing. The experiment seen from within looked like a tiny cosmos ticking forward through time. Same two photons, same entangled state, same physical system in both cases. One perspective, static, frozen, timeless. The other perspective, dynamic, evolving, temporal. And here is the part that physics is very firm about. Neither perspective is wrong. They are both correct descriptions of the same physical reality. They are both fully consistent with quantum mechanics. The external view and the internal view are not contradicting each other. They are complementary. Two valid ways of describing one thing, yielding completely different pictures of whether time exists. The time the internal observer experiences is real. This is important to be clear about, because it is tempting to hear all of this and conclude that time must therefore be an illusion, that if it only appears from one perspective, it must be somehow fake or constructed or less than real. That is not what the physics says. The time that emerges from the internal correlations is a genuine, valid, accurate description of the system. It is not incorrect. It is not a trick of perception. It is a real feature of the physical situation, just not a fundamental one, not a feature written into the bedrock of the equations, a feature that arises from within, from the relational structure of the entanglement, from the way one part of the system encodes information about another. Think about what that distinction means. Temperature is real. You can measure it. It affects physical processes. It causes things to happen. But temperature is not fundamental. It is not a property of individual particles. It emerges from the collective behavior of enormous numbers of particles interacting. Nobody says temperature is an illusion just because it is emergent. It is real and emergent simultaneously. That is exactly the status Mariva's experiment gives to time. Real, valid, measurable, and not fundamental. Time is what you get when you look at quantum correlations from the inside. Now here is the part where I want you to make it personal, because this is not just a story about photons in a lab in Italy. This is a story about you. You are a physical system. Your brain is a physical system. Your memories, the fact that you remember reading the earlier parts of this and can connect them to what you're reading now, are physical processes. Patterns of electrochemical state encoded in neural tissue. Correlations between the activity of billions of neurons, information stored in the physical structure of synaptic connections. Your sense of being located in a moment called now, of standing at the leading edge of your own timeline with a remembered past behind you and an anticipated future ahead. All of that is a physical process. It is happening inside your body, inside the correlations between atoms and molecules and electromagnetic patterns that constitute your experience of being conscious. You're not a soul floating in a river called time. You're a subsystem of the universe. And the time you experience the temporal flow that feels so immediate, so undeniable, so absolutely basic to what it means to be alive and aware, is a relational property. It is the experience of quantum correlations being read out from your particular vantage point inside the system. You are the internal observer. The rest of the universe is the clock. And the time you feel is what those correlations look like from where you are standing. I find that simultaneously destabilizing and strangely beautiful. Destabilizing because it removes the sense of being carried along by something external and universal. There is no cosmic river. There is no absolute now that you share with a galaxy on the other side of the universe. There is only the local, relational, correlation-generated time of your particular position inside the total quantum state of everything. But beautiful because it means you are not a passive passenger. You are part of the mechanism. The time you experience is being generated continuously by the physical relationships between you and the universe around you. Every interaction you have, every record your body makes of the world, every causal chain you participate in is a small act of time creation. You're not moving through time. In a very real physical sense, you're part of how time is made. The Morava experiment, the Page-Wouters mechanism, the Wheeler-DeWitt equation, the Landauer principle, the Oxford quantum dot results we talked about earlier, they all converge. They arrive at the same place from completely different directions. Time is not the stage the universe performs on. Time is something the parts of the universe generate for each other, through correlation, through entanglement, through the irreversible physical records that systems make of one another. You're not inside time. Time is inside your relationship with everything else. And here is what makes all of that even stranger. The experiments we have covered so far are, in a certain sense, the gentle ones. They show time being born, which is extraordinary enough. But there is another set of results, newer, more recent, coming from different labs with different methods, that show something beyond time emerging. They show time breaking, behaving in ways that even the relational picture does not fully prepare you for, ways that suggest the time you experience is not just emergent but fragile, contingent, structurally uncertain in ways that go deeper than anything we have discussed so far. And that is where we're going next. Part 10. Time is breaking in multiple ways. So we have established that time is not fundamental, that it emerges from correlations, that the arrow of time lives in records rather than in the systems being recorded, that a frozen universe can generate the full, vivid, undeniable experience of temporal flow from the inside, through nothing but quantum entanglement between its parts. That is already a lot to absorb. That is already, if you're being honest with yourself, a fairly significant rewrite of the mental model most of us carry around. But here is the thing. Those results, as strange as they are, still leave you with a version of time that behaves, that flows in one direction, that has a before and an after, that you can, at minimum, measure and track and reason about, even if its ultimate nature is more exotic than Newton imagined. The Page-Wouters mechanism and the Morava experiment and the Oxford quantum dot, they are all, in their way, stories about time being generated, time appearing, time emerging from something deeper. What I want to talk about now is different. Because in the last few years, from completely independent experimental directions, physicists have been finding something beyond time emerging. They have been finding time breaking, bending in ways it is not supposed to bend, doing things that even the relational emergent picture of time does not fully prepare you for. And the three results I am about to walk you through are, individually, each remarkable. Together they paint a picture of time as something far more structurally fragile, far more locally contingent, far more subject to the same quantum weirdness as everything else in physics than almost anyone was expecting. Let's start with temporal reflection, because it is the one that requires the most careful setup to appreciate. You're already familiar with spatial reflection. You look in a mirror every morning. Light travelling in one direction hits a surface, and instead of passing through, it bounces back in the opposite direction. The spatial component of the wave's propagation is reversed. This happens because the mirror presents an abrupt change in the medium, the transition from air to reflective metal, and waves encountering abrupt changes in their medium can reflect. This is standard, well-understood wave physics. It applies to sound, to water waves, to light. Nothing exotic here. Now ask a different question. If a wave can reflect in space, if the spatial component of its propagation can be reversed by an abrupt boundary, can the same thing happen in time? Can a wave encounter an abrupt change not in where it is travelling but in when, and reflect temporally? Can the temporal component of a wave's evolution be reversed? The mathematics of electrodynamics has always said yes, in principle. The equations permit it. But permitting something in principle and demonstrating it in a physical laboratory are two very different things, and until recently nobody had managed the latter. The challenge is that to create temporal reflection, you need to change the properties of your medium, the electromagnetic properties, the refractive index, faster than the wave itself can respond. You need the change to happen on timescales shorter than the period of the wave you're working with. For light, that period is on the order of femtoseconds, millionths of a billionth of a second. Achieving a controllable material change on that timescale, in a real physical substance, is an extraordinary engineering challenge. In 2023, a physicist named Heidi Musa and collaborators at the University of Regensburg met that challenge. They used a thin film of indium tin oxide, a material you have almost certainly encountered before because it is the transparent conducting layer on most touchscreens, and they hit it with an intense laser pulse that changed its electromagnetic properties almost instantaneously. A second light wave passing through the film at that moment experienced something it had never experienced before, not a spatial boundary, a temporal one, and it reflected. Not backward in space, but backward in time, its frequency shifted in ways that are the precise signature of temporal reflection, distinct from anything a spatial interface could produce, consistent with the theoretical predictions and with nothing else. This is not time travel. I want to be very clear about that because the phrase temporal reflection sounds like science fiction, and it is not. Causality is not violated. No information travels backward in time. What is happening is that the temporal structure of the wave's propagation, the way its oscillations are organized across time, is being altered by a boundary that exists in time rather than space. Time, in this experiment, behaves like a dimension that can have walls, reflective surfaces, boundaries that waves can bounce off. Which means time is not just something that flows, it is something that has structure, internal structure, the kind of structure that can push back. That is the first result. Now the second one, which comes from a completely different direction, and is, if anything, even more quietly unsettling. In standard quantum mechanics, transitions are instantaneous. When a particle jumps from one energy level to another, emitting a photon, absorbing a photon, changing its internal state, that jump happens at a moment, not across a duration. The particle is in state A, then it is in state B, and the transition between them is a point event in time, not an interval. The time that has duration is the time between transitions. The transitions themselves are zero-width slices of the timeline. This is not an approximation or a simplification. It is the actual mathematical structure of standard quantum mechanics. A group of physicists working under Hugo Dill at EPFL, the Swiss Federal Institute of Technology in Lausanne, decided to look at this assumption very carefully, and what they found is that it is wrong, or at least incomplete. Quantum transitions, when you probe them with sufficient precision, have intrinsic duration. The jump takes time. Not borrowed time, not time imposed on it by external conditions, but time generated from within the transition itself, determined by the internal properties of the quantum system, the energy difference between the states, the nature of the coupling involved. The transition carves out its own temporal interval through the dynamics of the quantum mechanical process. Think about what this means. Duration, the thickness of a moment, the how long of a change, is not something that exists between quantum events and is absent during them. Duration is something that quantum events produce. Each transition generates its own local temporal extension. Time, at the quantum level, is not a passive container that events occur inside of. It is a property that events create as they happen. If that sounds familiar, it should. It is the same theme we have been tracking all evening, showing up now at the level of individual quantum jumps. Time is not external. Time is not a background. Time is something physical processes generate from the inside as part of what it means to be a physical process. And then there is the third result, which is the strangest of the three, and which requires you to hold two ideas in your head simultaneously. The first idea is from general relativity. Time flows at different rates in different gravitational fields. Stronger gravity, slower time. This is experimentally confirmed, built into GPS systems, demonstrated at millimeter scales in the JILA lab we discussed earlier. The second idea is from quantum mechanics. A physical object can exist in a superposition of multiple states simultaneously. Both are true at the same time, in a quantum sense, until a measurement forces a definite outcome. Now put them together. A clock, a physical system that measures time, placed in a quantum superposition of two different gravitational environments simultaneously, not in one gravitational field or another, both at once, superposed. What does that clock read? The answer, according to both theory and a growing body of experimental evidence using atom interferometers and entangled photon setups, is undefined, not unknown, not uncertain in the way your location is uncertain when you have not checked GPS recently. Genuinely, physically, fundamentally undefined. The elapsed time registered by that clock is in superposition. There is no fact of the matter about how much time has passed. The duration itself, the geometric quantity that general relativity tells you is determined by your position in space-time, does not have a definite value when the position is in quantum superposition. Time, at the quantum gravitational frontier, can be indeterminate in exactly the same way that a particle's position or momentum can be indeterminate. It is subject to uncertainty principles. It can exist in superposition. It can be, in the most literal physical sense, both this value and that value simultaneously, until something interacts with the clock and forces a definite reading. Take all three results together, and the picture is stark. Time can reflect off temporal boundaries the way light reflects off mirrors. Time intervals are intrinsic properties that quantum transitions generate rather than external containers they occur inside of. And elapsed time itself can be quantum mechanically undefined when the physical system generating it is in superposition. This is not a picture of time as a river. It is not even a picture of time as a local, relational, emergent property that behaves itself once it appears. It is a picture of time as something genuinely fragile, something that can break, superpose, reflect, and dissolve back into the quantum indeterminacy from which it emerged. Something that is, at every level from the subatomic to the cosmological, far less stable and far more contingent than any of our intuitions about it have ever suggested. And if time is this fragile at the local laboratory scale, if it bends and breaks and goes quantum at the level of individual transitions and thin films of indium tin oxide, then what happens when you zoom all the way out? What does time look like at the scale of the universe itself? What does cosmological time look like when you apply the same scrutiny we have been applying to photons and quantum dots and gravitationally superposed clocks? The answer is that the universe's own clock is in trouble, and it has been for years, and almost nobody outside of cosmology has been paying attention. Part 11. The Cosmic Problem. There is a number that cosmologists have been arguing about for years. A number that, depending on who you ask, is either a minor technical headache that will eventually be resolved by better instruments, or one of the most significant cracks in the foundation of modern physics. The number is not exotic. It does not require any knowledge of quantum mechanics or general relativity to state. It is just a measurement of how fast the universe is expanding, and the problem is that when you measure it two different ways, using two completely independent methods, each one rigorous, each one backed by decades of careful observation and analysis, you get two different answers. Not slightly different. Not within the margin of error. Genuinely, stubbornly, embarrassingly different in a way that the statistics say should not be happening. The number is called the Hubble constant, named after Edwin Hubble, the astronomer who first demonstrated in the 1920s that the universe is not static but expanding, that the galaxies are racing away from each other, and the further away they are, the faster they are receding. The Hubble constant describes the rate of that expansion, how many kilometers per second faster a galaxy is moving away from us for every additional megaparsec of distance between us and it. A megaparsec, just to anchor the scale, is about 3.3 million light-years. We're talking about distances that make the distance from Earth to the nearest star look like a short walk to the corner shop. The first way to measure the Hubble constant is to look at the early universe, specifically at the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang, which permeates all of space in every direction, which has been travelling toward us for nearly 14 billion years, and which encodes in its subtle temperature fluctuations an extraordinarily detailed record of what the universe looked like when it was only about 380,000 years old. The Planck satellite, a European Space Agency mission that completed its observations in 2013, mapped these fluctuations across the entire sky with extraordinary precision. Cosmologists took that data, fed it through the standard model of cosmology, and extracted the Hubble constant. Their answer, approximately 67 kilometers per second per megaparsec. The second way is to look at the late universe, at objects in relatively nearby galaxies, supernovae of a specific type that always explode with the same intrinsic brightness, making them reliable distance markers. Cepheid variable stars that pulse in a predictable rhythm tied to their luminosity, allowing you to calculate exactly how far away they are. These are the tools of what is called the cosmic distance ladder, an observational tradition going back to Hubble himself, refined over decades of increasingly precise measurement. The answer from this method, approximately 73 kilometers per second per megaparsec, 67 versus 73, 9% difference. Write it out as a gap, 6 kilometers per second per megaparsec, and it sounds manageable. But in physics, what matters is not the size of the gap. What matters is the size of the gap relative to the uncertainty in each measurement. And when you run that calculation, when you ask how statistically significant this discrepancy is given how precisely each method has pinned down its value, you get 5 sigma, 5 standard deviations. In physics, 5 sigma is the threshold for claiming a discovery. It is the level of statistical confidence at which you say, this is not a fluke, this is not random noise, something real is happening here. The probability of a 5 sigma discrepancy arising by chance is roughly 1 in 3.5 million, and it has not gone away. That is the part that should concern you. This tension has been known and debated for the better part of a decade. Every time someone builds a better instrument, gets a cleaner data set, refines the analysis, the expectation is that the two values will converge, that one or both measurements will shift toward the middle and the tension will dissolve. Instead, the opposite has been happening. Both measurements get more precise, their error bars shrink, and the gap between them remains. The measurements are not converging, they are becoming more confidently different. This discrepancy is called the Hubble tension, and it is one of the most actively debated problems in all of contemporary cosmology. There are roughly 3 possible explanations. 1. There is a systematic error somewhere, some subtle bias in the Cepheid measurements, some unaccounted for effect in how the cosmic microwave background is being analysed. 2. There is physics missing from the standard cosmological model, some ingredient that affects the early universe's expansion, differently from the late universe's expansion. 3. Both measurements are correct, and the universe genuinely expanded at one rate in its early history and a different rate now, in a way that our current models simply cannot accommodate. The third option is the most radical and increasingly the one that some cosmologists are being pushed toward by the data. Which brings us to the second piece of the cosmic puzzle, because it turns out the Hubble tension is not the only thing suggesting the universe's large-scale temporal structure is more complicated than we thought. In 2024, the Dark Energy Spectroscopic Instrument, DESI, a remarkable piece of hardware mounted on a telescope at the Kitt Peak National Observatory in Arizona, equipped with 5,000 robotic fiber optic positioners that can simultaneously measure the spectra of 5,000 galaxies at once, released results from its first year of full operation. DSI's job is to map the three-dimensional distribution of galaxies across enormous volumes of the universe, measuring how cosmic structure has grown and evolved over billions of years. It is, in effect, a fossil record of how gravity and dark energy have competed to shape the universe over its entire history. Dark energy, if you're not familiar with it, is the name we give to whatever is causing the expansion of the universe to accelerate. When astronomers discovered in 1998 that distant supernovae were fainter than expected, meaning they were further away than a non-accelerating expansion would put them, they realized that something was pushing the universe apart. Not slowing it down the way gravity does, but actively speeding up the expansion. That something got called dark energy. In the standard cosmological model, dark energy is represented as a cosmological constant, a fixed energy density inherent to empty space itself, the same everywhere and at all times, unchanging across the entire history of the universe. A background hum of repulsion woven into the fabric of space-time. What DESI's first-year results hint at is that this fixed constant may not be fixed, that dark energy may not be constant, that its value may have been different in the past and may be different in the future, that the repulsive force driving cosmic expansion may be evolving over time, changing in strength, varying across the history of the universe in ways that the cosmological constant cannot account for. The statistical significance of this result is not yet at the 5 sigma threshold. It is a hint, a suggestion, a pattern in the data that requires more observation to confirm or rule out. But it is consistent across multiple independent analyses of the DSI dataset, and it is being taken seriously. Now sit with the implications of that for a moment. If dark energy evolves over time, then the rate at which the universe expands is not constant. It was different in the early universe, different in the middle epochs, different today, and potentially different again in the future. The expansion rate of the universe, which is, in the deepest sense, the cosmic clock, the large-scale temporal metronome that governs the pace at which the universe's own history unfolds, is variable. The universe does not have a fixed, uniform, well-defined tick rate. Its own temporal progression, at the largest scale we can probe, is uncertain in ways we do not yet understand. And here is the connection that I want you to see clearly, because it is the thread that runs through everything we have covered tonight. At the millimeter scale, in a Boulder laboratory, time flows at different rates across 2 centimeters of height. At the quantum scale in Oxford, the arrow of time lives in the measurement record rather than in the system. At the photon scale in Turin, time emerges from entanglement rather than from any external flow. At the quantum transition scale in Lausanne, time intervals are properties that events generate rather than containers events occur inside. And now at the cosmic scale, across billions of light years and billions of years of history, the universe's own expansion rate, its own temporal structure, is uncertain, variable, and potentially governed by a dark energy that is itself changing. Time at no scale is what Newton imagined. Not local, not human, not cosmic. Everywhere you look, across every order of magnitude, time turns out to be the same kind of thing. Local, relational, context-dependent, generated from within rather than imposed from without. The universe does not have a clock. It is, at every scale, improvising time from the inside using whatever physical relationships are available. And if that is true, if the universe genuinely does not have a reliable, universal, fundamental clock, then what does it actually mean to say the universe is 13.8 billion years old? We say that number with enormous confidence. It appears in textbooks and documentaries and museum exhibits presented as a settled fact. And in the context of the standard model, using the best measurements we have, it is our best answer. But it is an answer that assumes the rate of time's flow has been calculable and well defined across the entire history of the universe, and the growing evidence, from the Hubble tension, from DESI, from the quantum results, is that this assumption is shakier than it looks. These are not unanswerable questions. Cosmologists are working on them actively, urgently, with some of the most powerful instruments ever built. But they are also questions that no cosmological model currently in existence can fully resolve. And the honest answer, the one that physics arrives at when you press it hard enough, is that the cosmic time of the universe has the same fundamental status as the quantum time of an electron in an Oxford laboratory. Real at the local, relational level, undefined at the absolute universal level, not the backdrop, never the backdrop, always the product. Which means we have arrived finally at the hardest question of all, not how time behaves, not where the arrow comes from, not why the universe's clock is uncertain, but what time actually is. What physicists, after all of this, actually think it is. And the answer to that question is not a single clean statement. It is a disagreement between some of the most serious minds in theoretical physics, a disagreement that has been sharpening for decades and has never been resolved. And the shape of that disagreement, it turns out, tells you more about the nature of time than any single experiment we have discussed tonight. Part 12. The Final Question. Carlo Rovelli has spent his career arguing for a position that can be stated simply, though its implications are not simple at all. He says that time, as we experience it, flowing, directional, divided into past and future, carrying the weight of memory and anticipation, is not a fundamental feature of reality. It is something that emerges at the scales we inhabit, from the thermodynamic properties of the systems we're made of and interact with, from the relational correlations between subsystems of the universe, from the irreversible records that physical systems make of each other. At the fundamental level, in the equations of quantum gravity, Rovelli argues, time simply does not appear. It is not there. The universe, at its most basic description, is a static network of quantum correlations. Time is something that arises from this network when you zoom in to the level of a physical observer embedded within it. Time is the name we give to the correlational structure of the universe as seen from the inside. In this view, the experience of time flowing, the feeling of being carried from past to future, of standing in a present moment with a remembered history behind you and an anticipated future ahead, is a thermodynamic and relational phenomenon. It is real in the same way that temperature is real. Temperature is not a property of individual particles. Individual particles do not have temperatures. Temperature is a statistical property that emerges when you have large numbers of particles interacting, and you want to describe their collective behavior. But temperature is not an illusion. It is real. You can measure it. It affects physical processes. It is just not fundamental. It is emergent. And Rovelli argues time is the same kind of thing. Emergent, real, not fundamental. Lee Smolin, a physicist at the Perimeter Institute in Waterloo, Canada, takes a profoundly different view. For Smolin, the timelessness of the Wheeler-DeWitt equation is a symptom of a flawed approach rather than a deep truth. He argues, most forcefully in his work on what he calls the reality of time, that time is the most fundamental thing there is, that equations that eliminate time are not more fundamental than equations that include it, they are less fundamental. They have abstracted away the very property of reality that makes physics real rather than purely mathematical. For Smolin, the universe is fundamentally a temporal process. The laws of physics themselves may evolve over time. The constants of nature may not be constant, but may have values that were determined by the universe's temporal history. In this view, time is not something that emerges from a timeless substrate. Time is the substrate. Everything else is what emerges from time's flow. And then there is John Archibald Wheeler, the physicist who collaborated with DeWitt on the equation bearing his name, and who spent the last decades of his life developing what he called the participatory universe. Wheeler argued that reality itself is not fully formed and predetermined in the absence of observation, that the universe is, in some meaningful sense, brought into being by the act of observation. that observers are not passive witnesses to a pre-existing reality, but active participants in the creation of that reality. He captured this in a phrase he used often, it from bit, the idea that physical reality, the it of the universe, is derived from informational processes, from the bits of yes or no questions that are answered by every measurement, every interaction, every observation. For Wheeler, time and reality are woven from acts of observation. The universe is participatory. It creates itself through the acts of internal measurement that it performs on itself. These three positions, time as emergent thermodynamic structure, time as the fundamental real thing, time as the product of participatory observation, are not fringe views. They are positions held by serious theoretical physicists, backed by serious mathematical work, and all of them are compatible with the experimental results we have discussed tonight. None of the experiments rules out any of the three. The photon time experiment is consistent with Ravelli's emergent time. It is also consistent with Smolin's fundamental time. It is also consistent with Wheeler's participatory universe. The Oxford quantum dot result fits all three. The Wheeler-DeWitt equation is consistent with all three interpretations, though it motivates them differently. This is not a failure of physics. It is the frontier of physics. It is the place where the equations run ahead of interpretation, where the experiments confirm predictions without confirming the conceptual picture behind those predictions, where multiple incompatible worldviews make the same observational predictions, and there is as yet no experiment that can distinguish between them. But notice what all three views agree on. They all agree that time as Newton conceived it, an absolute universal external backdrop flowing uniformly through the cosmos, is wrong. They all agree that time is in some sense local, relational, dependent on the physical context of each observer and each measurement. They all agree that the direction of time is not fundamental but emergent. They all agree that the experience of temporal flow is connected, in deep and non-trivial ways, to the thermodynamics of observation and the quantum mechanics of correlation. Ravelli and Smolin and Wheeler disagree about whether time is ultimately emergent or fundamental, but they all agree that the naive picture of time as a river carrying the universe along is not what physics describes. And here is the synthesis that emerges from everything we have traced tonight, from the aluminum ion clock in Boulder, to the photon experiment in Italy, to the quantum dot in Oxford, to the cosmological tensions in the data from DSI and Planck. Time, as far as current physics can determine, is local. It is the property of a specific location in space-time geometry, varying from point to point, detectable as a difference across 2 centimeters of height in a Boulder laboratory. Time is relational. It emerges from the correlations between physical subsystems, from the quantum entanglements that one part of the universe forms with another, from the way the state of one system encodes information about another. Time's direction is recorded. The arrow of time lives in the physical memories that systems create of each other, in the thermodynamic irreversibility of measurement, in the entropy generated every time any physical system makes a record. And time, at the most fundamental level described by our best equations, may not exist at all, may be a feature of the internal view from inside the universe, rather than a feature of the universe's fundamental description. You're not moving through time. Time is something that is happening between you and everything you interact with. Every thought you have is a physical record. Every memory you hold is a thermodynamic scar. Every moment you experience as now is the local, relational emergence of temporal structure from the quantum correlations between your physical state and the physical states of the universe around you. The past is not behind you in some external river. The past is the set of irreversible records encoded in the physical structure of your body and your environment, the thermodynamic traces of interactions that have already happened, held in matter, not in time. This is not science fiction. This is not metaphysics. This is the conclusion that serious theoretical physicists are being pushed toward by a convergence of experimental results that would have been impossible to produce even 20 years ago. The aluminum ion clock made it possible to see time dilation across 2 centimetres. The Oxford quantum dot showed the arrow of time living in the record. The Italian photon experiment showed time being generated by entanglement. The cosmic tension in expansion measurements shows that even the universe's own clock is uncertain. Each of these results, from completely different experimental traditions, from completely different scales and systems and methods, points toward the same place. Time is not something the universe has. It is something the universe makes, continuously, through the act of physical systems coupling to each other, correlating with each other, recording each other, entangling with each other. Every interaction is a small act of time creation. Every measurement is a moment of temporal genesis. Every irreversible record written into the physical fabric of anything is a brick in the structure that you experience as temporal flow. The universe is not aging inside time. The universe is generating time as it ages. The two things are the same process, seen from inside and outside simultaneously. And here is the thought that I cannot quite let go of, the one that sits at the back of everything we have covered tonight. If time is relational, if it emerges from the quantum correlations between systems, then the universe is, in a very literal sense, its own timekeeper. Not because there is some special clock at the centre of everything, not because there is some privileged reference frame that defines the true now, but because every pair of interacting systems is a clock for each other. Every entangled photon pair is a small universe generating its own small time. Every measuring apparatus coupling to a quantum system is a temporal act, a moment of before and after being carved from what would otherwise be a static wave function. The universe generates time from the inside by paying physical attention to itself, by the vast network of interactions and correlations and measurements and records that constitute physical reality at every scale from the subatomic to the cosmological. The aluminum ion in the Boulder vacuum chamber, ticking 19 decimal places out, is not measuring time the way a ruler measures a wall. It is participating in the process by which time is made. It is one of an uncountable number of physical systems in the universe that are right now generating the temporal structure of reality through their physical state transitions and their quantum correlations with their environments. Every tick is not a reading of a pre-existing time. It is a small creation of temporal fact, a moment of relational physics carving a before and an after out of what the equations say is, at bottom, a timeless quantum state. You are doing this too. Every memory you form is an act of time creation. Every causal chain you participate in, every event that leads to another event in your life, is a piece of the universe paying thermodynamic attention to itself through your physical existence. You're not a passive passenger riding a river called time. You're part of the mechanism by which the river exists at all. The clock didn't just measure time. It revealed that time might be something the universe is doing, something it never stops doing, something it does through every interaction and every correlation and every irreversible record, from the collision of two quarks to the slow drift of galaxies across billions of years. And if that is true, if time is something the universe continuously generates rather than something it passively inhabits, then asking what time is the same as asking what the universe is doing right now. The answer is, it is creating the next moment, the same way it has always created every moment, from the inside through the act of being physical. And that might be the most remarkable thing physics has ever told us. Not that time is an illusion, not that time does not exist, but that time is something stranger and more intimate than either of those things. Time is the universe noticing itself. Time is what happens when the cosmos turns its attention inward, through the medium of physical interaction, and generates the before and after that make change possible, that make memory possible, that make you possible. The clock in Boulder is still ticking, 19 decimal places of precision, sensitive enough to see the curvature of space-time across the width of your thumb, and somewhere in that extraordinary precision, if you look carefully enough, you can see it. The hint that what the clock is really measuring is not a thing that pre-exists and flows. What the clock is measuring is the universe generating the next moment, one quantum transition at a time, from the inside of a reality that has no outside, in a cosmos that is its own clock, its own observer, and its own time.